Water is an essential matter for our daily lives. Every day, we are living in contact with water, not being conscious of it, but water is offering us numerous benefits. Life, with a wealthy supply of water, this is the very thing we wish for. And we cannot forget machines working behind the water supply. They are pumps. Pumps are precious apparatuses which support our daily lives. They have been developed as machines which lift water from low places to high places. And then, pumps have been developed rapidly together with evolution of motors to transfer big volume of water to very high locations where nobody could imagine ever. Among various types of pumps, the most generally applied are volute pumps. Now, let me introduce you the volute pump, which has both great performance and wide applicability. Pumping principle of volute pump. The volute pump is a pump which rotates an impeller in it and transfers water utilizing centrifugal force generated by it. The pump transfers water by performing two actions at the same time. These are discharge action and suction action. Firstly, let's make an experiment of the discharge action using a simple equipment. When an impeller is rotated in water, water level in the center falls and that of the periphery rises. This is because centrifugal force generated by impeller rotation pushes out water to the outside. Mechanism of the volute pump is similar to this equipment, and the pump transfers water utilizing centrifugal force generated by impeller rotation. The second consideration is about the suction action. This is an experiment to see the atmospheric pressure. A glass test tube filled with mercury is vertically set in a container also filled with mercury. The column of mercury in the tube then maintains its height of 76 centimeters. This is because the atmospheric pressure acting on the mercury surface in the container pushes up mercury in the tube. Every surface contacting the air receives the atmospheric pressure. For water, the column height becomes as high as 10.3 meters because of less specific weight. When you drink juice using a straw, the action is explained by the same theory. The atmospheric pressure actually pushes juice surface, and the juice is suctioned through the straw to your mouth. The volute pump suctions water using this force of the atmospheric pressure. Now, let's see how water is transferred by the volute pump watching an animation. When the impeller rotates in the pump, the interior water is pushed out to the casing by centrifugal force and discharged. Besides, pressure at the pump center becomes negative. And the atmospheric pressure working on the suction water surface pushes up water to the low-pressured pump. In such way, the volute pump performs suction and discharge actions simultaneously by rotating its impeller to generate negative pressure and centrifugal force. The volute pump can pump water from a low level to a high level by these actions. Construction of volute pump. Pumping action by the volute pump is mainly carried out by 4 parts. These are an impeller, a casing, a suction port, and a discharge port. The impeller is the most important part to apply centrifugal force to water by its rotation. The casing is a part to collect water from the impeller and discharge it. It is constructed strongly to secure from pressure. The suction and discharge ports are parts to suction and discharge water, as their names suggest. The pump casing has to be filled with water prior to operation. For this, a priming port is provided on the upper part of the casing. Water is poured from the priming port, and the interior of the pump casing and suction pipe is filled with water. Now, we look through the other parts too. Liner rings are provided to maintain small gaps between the impeller and casing, and to minimize leak of pressurized water from the discharge side to the suction side. They are fitted on the entrance and rear sides of the impeller and casing. To avoid leak of pressurized water inside the casing, gland packings or a mechanical seal are popularly used. The gland packings are made of special fiber impregnated with lubricant. Small amount of water leak is allowed to prevent shaft seizure. In contrast with them, construction of the mechanical seal is designed to minimize leak of pressurized water to an invisible level. The gland packings and mechanical seal are installed at a portion where the shaft penetrates the casing. A shaft is a part to transfer motor torque to the impeller. The shaft has sufficient strength to withstand various forces acting on it. Stainless steel and carbon steel are typical materials of the shaft. Bearings support weight of the shaft and impeller and force generated by pump operation. Ball bearings are popularly applied. A bearing housing accommodates the bearings and locks their outer rings for smooth shaft rotation. Lubrication oil was essential to minimize friction and wear and to prevent shaft seizure. However, recently sealed type ball bearings are popularly used. Grease is sealed in them to reduce effort of oil replenishment. The pump and motor shafts are connected by a coupling with coupling bolts, which transfer motor torque to the pump. It is installed on pump and motor shaft ends. Characteristics of the volute pump. Pump performance is defined by relationship of capacity and head. A capacity refers to quantity of liquid discharged from a pump per unit time. A head represents liquid energy given by a pump in a unit of liquid height. Full head difference between suction and discharge ports of a pump is referred to as a total head. In a graph with the total head in the vertical axis and the capacity in the horizontal axis, a downward sloping curve is drawn as shown. The curve is named HQ curve. The HQ curve varies depending on impeller configurations, sizes, rotation speeds, and so on. When the impeller diameter increases, the HQ curve rises. It depends on the impeller configuration, but the capacity and total head generally change proportional to square of the impeller diameter ratio. The pump performance changes with the number of impeller stage. When the number of impeller stage increases, a total head at a certain capacity increases by the number. Even with the same impeller, the pump performance changes when the rotation speed changes. The HQ curve rises as rotation speed of the impeller increases. The capacity changes proportional to the rotation speed ratio, and the total head does the same to the square of the ratio. Power is required to rotate the impeller and to operate the pump. Work done by a pump is converted and calculated from the product of the capacity and total head. The work is called theoretical power or liquid power. However, a larger power than this is required because of pump internal losses and resistances. This actual power required to operate a pump is called shaft power. In a graph, with the shaft power in the vertical axis and the capacity in the horizontal axis, a smooth upward sloping curve is drawn. The driving motor should have an output larger than the pump shaft power. The rate of work done by a pump, or the theoretical power against the shaft power, is named pump efficiency. In a graph, with the efficiency in the vertical axis and the capacity in the horizontal axis, a mountain-shaped curve is drawn as shown. A pump has to be operated at a capacity with high efficiency. A high-efficiency range can be cut out from an HQ curve for a pump. And select-in chart is arranged as shown. The chart can be a quick reference for pump users to find a suitable pump meeting their capacity and total head requirement. Such charts are found in production catalogs for pump model selection. Each pump has a nameplate on it to show pump ratings specified by the pump manufacturer, such as the capacity, total head, and motor rotation speed. Head loss and total head. In pumping facilities, piping and valves play important roles, as well as pumps themselves. Such valves include a foot valve, check valve, and sluice valve. When flowing in piping, water meets resistance caused by friction against piping walls and flow disturbance. A loss of pressure by such piping resistance is called head loss. The head loss increases by rust development and scale accumulation in piping. In a graph, with the head loss in the vertical axis and the capacity in the horizontal axis, an upward parabolic curve is drawn. The curve is called resistance curve. since the head loss is proportional to square of flow velocity. The value at a certain capacity changes when piping size differs. A pump is operated at the intersection of an HQ curve and a resistance curve, and it is called operation point. The pump discharges capacity at the operation point. Valve throttling is the most popular method to control capacity, and it can be explained as valve throttling increases the resistance to enlarge the head loss and decreases the capacity. When a pump transfers water to a certain height, a level difference between the suction and discharge water levels is called actual head. And the sum of the actual head and head loss is equivalent to total head. A head, as a characteristic of a pump, should be this total head. As a total head is the sum of an actual head and head loss, a total head graph of a certain piping system is illustrated as shown here. Parallel operation and series operation. When pumping water, more than one pump can be connected by piping. For parallel operation, discharge of more than one pump converges into a single discharge piping. And for series operation, the discharge pipe of the first pump is connected to the suction of the second pump. When two pumps with the same characteristics are operated parallel, the capacity corresponding to a certain total head becomes double of the single pump operation. However, some measure, such as enlargement of the discharge piping, is necessary because the increased total head by the increased head loss prevents the capacity to be doubled. When two pumps with the same characteristics are operated in series, the total head corresponding to a certain capacity becomes double of the single pump operation. The second pump, however, receives a high compression pressure at its suction, and the pump model should be selected checking the allowable pressure. Suction performance. Water typically boils at 100 degrees Celsius. Have you ever heard that it boils at a lower temperature at a high mountaintop? At the top of Mount Fuji, water boils at 85 to 90 degrees Celsius because of the lower atmospheric pressure. As such, water boiling temperature varies depending on the atmospheric pressure. During pump operation, pump inlet pressure drops partially, and if extreme, water in the pump boils. This phenomenon is called cavitation, and vapor bubbles generated by boiling lower the pump performance significantly. Cavitation also causes vibration and noise and may result in pump damage. In order to operate pumps without cavitation, it is required not to make the pump suction pressure too low. The 10.3 meter atmospheric pressure on the suction water surface is reduced by a head loss consumed at the pump inlet, as well as the suction lift and head loss, and the remaining pressure should not drop to the boiling level. This pressure consumed at the pump inlet is named NP NPSH required, and its value is given for each pump and each capacity. NPSH required usually decrease for smaller capacity and tends to be small for lower rotation speed. Less NPSH required value means better suction performance. Also, water temperature is an important factor in consideration of suction performance. When water temperature rises, its boiling pressure level increases. Thus, the remaining pressure after deducting each factor from the atmospheric pressure is necessary to be larger. This graph shows relationship of water temperature variation and suction lift. When water temperature rises, suction from a lower level cannot be attained. Pumps give us cheerful lives. They promise us comfortable lives. Water is transferred to the top of high-rise buildings by pumps. For agriculture, and for fisheries, and for industries, pumps are successfully working. Ebara Corporation is a comprehensive manufacturer of pumps and appreciates the fundamental technologies of the Volute pump's grassroots, and are making efforts of further R&D and quality improvement. Ebara continues to deliver numbers of pumps to the world and support people's daily lives.